Hello there everyone, and thank you for joining me today. Today we are going to discuss the average value of a function on a given interval. So from a calculus perspective, we can find the average value of a function on an interval using the formula provided inside of the box there. If f is integrable on the closed interval from a to b, then the average value of f on the interval is 1 over b minus a times the definite integral from a to b of f of x dx. Think of average value like the average y value, the average height of the function, if you will, right? So let's think about this from an algebraic perspective, like from the formula, and then from a graphical perspective using the image down below. Okay, by looking at the formula from a more kind of algebraic perspective, I guess, if you want to find the average value of something, the average points per game for a basketball player, you add up all the points and divide by the number of games, right? Well, here, if we're finding the average y value, let's add up all the y values and divide by the number of y values. And when we first talked about definite integrals, that's how we talked about this definite integral as, a Riemann sum of all of the heights of those rectangles that we first used to estimate the area under a curve. And then 1 over b minus a is the, 1 over the length of that interval. There's the divide by the number of y values portion of that red text there. So from a more algebraic perspective and, knowing what you know about averages, hopefully this formula makes a little bit of sense. From a more graphical perspective, and this image does a decent job of showing it, to find the average value of a function f of x on a given interval from a to b, remember that's kind of the average height or the average y value, what we can do to visualize this is take the area under that curve f of x from a to b and stretch it out to form a rectangle with the same area and the same length, that length going from x equals a to x equals b. Well, if you do so, maintaining the same area and the same length, the height of that rectangle then is that average value of f of x. And I think the diagram does a pretty good job of showing how the height of that rectangle looks like, the average y value of that purple curve from x equals a to x equals b. So there are two attempts from me to try to describe this formula and how we go about using definite integrals to calculate the average value of a function on a given interval. If those hit home, great. If not, we can work on it a little bit more, but if anything else, we have to at least understand how to calculate average value and how to work with it. So let's practice that, and we'll do some calculator problems and some no calculator problems. Here's the first. The temperature F in degrees Fahrenheit of a cup of coffee, T minutes after it's poured, is given by the function capital F there. To the nearest degree, what is the average temperature of the coffee between T equals 0 and T equals 10? Okay, average temperature, and the function f gives the temperature. So here we are finding the average value of that function f from t equals 0 to t equals 10. I've seen various notations for this. Okay, here's the one I'm going to use. We've got this function f. We're going to find the average value of it, right? And we're finding the average value from t equals 10 to t equals 0. Well, here's our a and our b in our formula. So let's get it set up. Using the formula from the last screen there, this is 1 over b minus a, 1 over 10 minus 0. That's the dividing part of this average calculation. Okay, here now the definite integral from 0 to 10, and then our function f is this function, and rather than rewriting the whole thing, like if I'm going to save time on a free response question, this function f is already named, so I'm just going to write it down here. Of course, when we go to use our calculator, we'll have to actually type this in, right? But to save a little bit of time in this video, I'll just write down capital F there. Now we've just got to run the numbers, right? So we take a graphing calculator, we use that option in the math menu that allows us to run definite integrals, and of course we can't type in capital F, we have to type in the actual function itself, unless you've stored that into the y equals menu, in which case you can recall it like we've done in class before. Okay, but if we run those calculations, and we go to the nearest degree, like it says here, the final answer is choice D here, 149 degrees. If you run this, it ends up being 148.820, and then to the nearest degree, then rounding up to 149. To check whether our answer is reasonable or not, we've got this cup of coffee, after we pour it out, of course, it's going to cool down, and that's why this exponential function has a negative exponent for what it's worth. But to give you some sense of our answer being reasonable, I went ahead and I calculated F of 0. That's the temperature of the coffee when it's first poured out, and that ends up being exactly 190. And then if you calculate F of 10, if you plug 10 into the function F, you get 118.557, right? So when the coffee is first poured out, it's got a temperature of 190. 10 minutes later, the temperature is, about 120. So to say that the average temperature on that time frame is in the middle, 148-ish, is reasonable here. So just to give a sense of whether our answer is reasonable or not, I thought I would provide that information. So here was a calculator question about average value. We just have to basically know the formula and how to calculate it and how to use our calculator correctly. But let's try a no calculator question. Let f be the function defined by f of x equals 1 over x. What's the average value of f on the interval from x equals 4 to x equals 6? Well, here's our a, here's our b. Let's get our formula set up. We've got this function f when we're finding its average value. Using that as kind of a subscript there. That'll be 1 over b minus a. That's 6 minus 4. That's the length of our interval, 1 over the length of our interval. So we're dividing by the length of our interval. From x equals 4 to x equals 6. And we're looking at the area under this curve right here. Well, we don't have a calculator this time, and that means we'll have to evaluate this definite integral using antiderivatives like we practiced previously. And an antiderivative for 1 over x is the natural log of the absolute value of x. And we'll be able to drop those absolute value symbols because we're going from 4 to 6. That's a positive bunch of x values there, right? So applying that fundamental theorem of calculus, here we go. We've got our 1/2 times the natural log of 6 minus the natural log of 4. Okay, and you can see that itself doesn't match up with any of our multiple choices. So, like we've seen before in this calculus class, sometimes we've got to recall properties from pre-calculus or even algebra 2. Here's a property of logarithms that says if you have 2 logs of the same base and you are subtracting those logs, you could condense that down to a single logarithm using a quotient, like I have here. So, applying that to this blue example, if we have 1/2 times the natural log of 6 minus the natural log of 4, we can condense that difference down to the natural log of 6 divided by 4, where 6 divided by 4 reduces down to 3 over 2. And that is one of our multiple choices right here, this choice C. So here was a no calculator question requiring us to calculate the average value of a function. Okay. Of course, not every such question would have natural log as its antiderivative. Some might be a little bit more intense with the fraction work when you get to this step down here. Okay, but this one gets the idea across of how we calculate that average value without a calculator. Now, of course, in true, AP style, we might run into some questions that require a little bit more problem solving, and there might be various other iterations of this question right here, but here is at least one question that's going to require us to do a little bit more problem solving rather than just using the formula to evaluate. So here, if the function f is given by x cubed, and it has an average value of 9 on the closed interval from 0 to k, then k equals one of these multiple choices, all right? If we had enough time, we could, of course, work backwards from the answers. That would require us to plug in a bunch of these, and that might be a little bit more time-consuming than we want. So let's try to approach this problem more straight on. And this question is discussing the average value of this function f. So a fair place to start would be to kind of get this laid out and write down our formula for that. And here again is that formula from previously in this lesson. This is it. This is the average value of function f on the interval from x equals a to x equals b. Okay, well, what do we know about this situation? We know that this function has an average value of 9. So I can plug that in right here. And it's got an average value of 9 on the closed interval from x equals 0 to x equals some constant k. Well, let's plug those values in for a and b respectively. So this will be 1 over k minus 0 times the definite integral from 0 to k. And we know what f of x is. It's x cubed. So I have taken the average value formula and plugged in everything we know to it. The idea is that we're now going to be able to solve for k somehow. Well, let's play this out a little bit. Here's 9 equaling k minus 0 is k, so we have 1 over k there. This piece here tells me to use antiderivatives. So here goes. An antiderivative for x cubed would be x to the 4th over 4. And we're evaluating that from x equals 0 to x equals k. Well, this 1 over k business here is fine where it's at, but remember k is some constant, and I'm trying to solve for it. This is kind of jamming me up right now, so I'm going to take that 1 over k and just multiply it to the other side for the time being. You might find that wasn't the step that you would take there. That's just going to help me focus on this right-hand side a little bit more. So what I have left on that right-hand side is this stuff in the circle here, all right, where we now have to plug in k and plug in 0. So here goes. This is k to the 4th over 4 minus 0 to the 4th over 4. And of course, 0 to the 4th over 4 is going to be just 0. So that gets me this far. And if I want to solve for k, I'm going to want to get all the k's on the same side eventually, but this 1/4 on the right-hand side is kind of jamming me up now. So maybe I multiply both sides by 4 to get me this much here. And now I can start to see a strategy in my head. If I get all the k's over to the same side now, your thought might have been to divide by k right there, but when we divide by a variable, we eliminate 0 as a potential solution. And we'll talk about that more in a moment. So rather than divide by k, let's get all the k's to the same side so that we can now try to solve by factoring, where I take a k out of this expression, leaving me with k cubed minus 36. And now if I set my factors equal to 0, one of those solutions is 0, and the other one would be eventually what looks like the cubed root of 36. Now we got two solutions here, but let's talk about this one for a moment. If k were equal to 0, we would be evaluating this definite integral from 0 to 0, which would give us 0, and then we would be getting 0 for our average value. But even beyond that, k can't be 0 because I have k in a denominator right here. So k equals 0, while it is a solution to this equation here, it is not a valid solution to the overall situation here, which leaves me with the cubed root of 36, and using exponential notation, that is this choice E right here. So here's a problem where we used average value and had to problem solve a little bit in order to solve for a given value k. There will be different variations of this type of problem with average value, but here is at least one example to get our momentum going with all of that. So that's enough right now about the average value of a function from a calculus perspective. Thank you for watching.